So let's go ahead and just start off with your background. Tell us a little bit about yourself.
Yeah, so I am currently an assistant professor of machine learning at CMU. I kind of work broadly in reinforcement learning, and I guess I just to kind of go over my background, I did my undergrad back in India in at IIT Bombay. After that, I did my PhD at UC Berkeley, and then I spent some time at Google DeepMind as a research scientist, and then after a year, so I took a gap year of one gap year, and then after that, I started my faculty job here.
Mhm.
Yeah, I think that's kind of broadly it. I can go into things that in more detail, but yeah.
Yeah, awesome. So let's go ahead and start off with your time in undergrad. So, you were at IIT Bombay from 2014 and 2018. You were advised by Professor Sunita Sarawagi. Maybe just tell us a little bit about your experience there, some of the research that you did there as well.
Yeah, that's that's a long time ago.
Yeah.
But yeah, I guess I started off. So back when I was an undergrad, the like sort of like the first wave of deep learning was kind of still very hot, and people were working. People were starting to work more in deep learning
Hmm.
architectures, things like this. I think in 2017, the attention is all you need paper came out, and that was sort of like
Right.
starting to become big. A lot of the research could be done in machine learning on very tiny GPUs back then, which
Hmm.
is not the case now. But I actually started out doing research in formal methods and some kind of some things adjacent to theoretical computer science.
Hmm.
I did that in my sophomore year a bit, and after that moved to doing sort of more machine learning and AI. Actually, the nice thing was I kind of didn't know which area of ML to work on, so I got a wide experience across many different areas.
Hmm.
So we with Sunita, we kind of ended up working on things involving sort of calibration of models. And how can you make sort of machine learning models more calibrated to uncertainty? We actually published a paper on that as well at ICML, I think in 2018, if I remember correctly.
Hmm.
We ended up doing that for like transformers and just sort of machine translation systems. That was kind of the best thing you could have done back then.
Hmm.
So you can translate English to German and things like this. And
Hmm.
back then, models were like really terribly calibrated.
Hmm.
And if you ran an autoregressive model and asked it to decode over very long, reasonably long sequences, even, it would just not do well at all, which is
Hmm.
not the case anymore. Things have changed a lot since then. But I also actually, in my undergrad, I did get an opportunity to intern at Google Brain.
Hmm.
And this was the time when Jeff Hinton was starting his team in Toronto, and I kind of ended up getting the fortunate opportunity to be one of his interns back then. And unlike sort of Jeff's past work, we ended up actually exploring things involving reinforcement learning. So that was
Hmm.
my first foray into RL. And that project was more around sort of like hierarchical RL, so like having a system of agents which are sort of managed by other agents. So it's kind of like a feudal system. There's a manager agent and there's some worker
Hmm.
agents trying to do some tasks. There was also the time when TRPO had just come out, and I
Hmm.
remember reading that paper very vividly and implementing a lot of policy-based methods and sort of just getting to learn more about what RL or what deep RL is all about. Since
Hmm.
then, deep RL has evolved a lot as a field,
Hmm.
and even that doesn't look the same as what it used to be back in the
Right.
day. But we had these tiny little grid worlds that we were looking at back then. So that was
Hmm.
sort of my rough sense of research in undergrad. And then I think just like looking into a lot of these things in undergrad, I realized that I think I was drawn more towards areas which had more sort of fundamental questions which could potentially require some amount of like theoretical thinking, not necessarily like proving theorems, but just
Hmm.
thinking about it more conceptually, as
Hmm.
well as things which could kind of work very well. And that sort of naturally drew me to more of RL, and that's kind of what I did my PhD in later.
Hmm. Awesome. So maybe tell us a little bit about your experience applying to PhD programs, how you sort of decided that Berkeley was the right fit, how you decided that Sergey, who's obviously incredible, was the right fit, and what you ended up focusing on.
Yeah, that was also very different from time now because
Yeah.
now I'm on the other side and I recruit students for my lab and
Right.
that's kind of very different. But back when I was applying, I sort of I ended up so I was obviously applying from India.
Right.
I got the opportunity to work in sort of a lab in sort of North America with
Hmm.
Google Brain back then. So I
Right.
kind of had enough sense of like how research goes in the US. So I had some understanding of like what that was. Um, But what I kind of roughly knew that I was interested in questions involving kind of more conceptual ML things that I just described. So I did a very selective PhD application process actually. So I applied to grad school. I think I had applied to 7 schools or so, if I remember correctly. Out of which 3 or 4 were actually master's programs because I didn't know whether I would get into a PhD or not. I had like sort of a one paper at a NeurIPS workshop in machine learning, and I had one paper at sort of out of some past work in formal methods actually.
Yeah.
And that was kind of fairly normal for back then, unlike now when you see so many
Yeah, of
papers
course.
on a person's resume. But so I ended up I ended up applying to only a couple of schools for a PhD, which included, I think, Toronto, CMU, Berkeley, and maybe one more, I think, and a bunch of master's programs. Because I was not sure if I kind of would get through in a PhD program, and also if I did get through, would I kind of want to work in a totally different area because I was somewhat a bit tied towards more conceptual things. And obviously back then, I think I got offers from all these 3 schools like Toronto, Berkeley, and CMU. And Berkeley seemed to be kind of a good fit because I was really drawn towards RL, as I just mentioned, because of the reasons I just talked about a bit ago. So that was sort of my journey into kind of getting into Berkeley. At Berkeley, I think it was pretty clear that I sort of was interested in RL, and I didn't really look through to work with necessarily like other advisors. Sergey was obviously awesome. I had a lot of interesting discussions with him back then, and it was fairly clear that I would kind of work with him, collaborate with him. So yeah, that's kind of how I got to working with him, and then yeah, I think my research has taken a lot of turns through the years. So like it
Right.
started off with like problems involving exploration in RL. I was actually looking at these tasks of like how can we train policies to do better exploration, to collect the right data to learn from. But then I realized, I think, in the course of that project, that actually policy optimization algorithms we have right now cannot even learn from data that has been collected, and that kind of went into sort of this whole bit about offline reinforcement learning that a lot of my
Right.
PhD is on. Now I think again, like we have very strong priors in models, and sort of the same question is somewhat, I would not say like fully in some ways disconnected, but like somewhat getting back towards the question of exploration quite a bit. So a lot of my more recent work from my lab has been more around exploration as a whole. But that's sort of roughly what kind of how I got into PhD and my process, my experience applying.
Yeah, awesome. So, I mean, you were at Berkeley from, let's call it 2018 to 2023. And throughout that
Yeah.
time, you were also a student researcher at Google Brain, where at Google Brain, I
So
think you were working on like
yeah,
large-scale applications of offline RL and data-driven design with several collaborators. This is from
yeah,
June 2020 to March 2023. Maybe tell us a
yeah.
little bit about how you sort of balance Google Brain and working with Sergey.
Yeah, yeah. So actually, yeah. So I was not there from 2018 to 2023. I was there from
Yeah,
2020 to
right,
2023.
right.
I so actually the point was that I mean a lot of my again back then I think a lot of there was a lot of collaboration between industry and academia,
Yeah,
just because Google Brain back then was a lab focusing a lot more on fundamental research, and I knew some people there from for instance from my internship and people I talked to during my internship before starting my PhD. But then what ended up happening was actually that some of my very first papers in my PhD, I collaborated with George Tucker, who's actually still at DeepMind, who's
yeah.
a research scientist there, and he was also back then interested a lot in like questions around offline RL and offline decision making. So we ended up collaborating a lot there, and that sort of naturally became a pathway to sort of working at Google as a part-time student researcher. Sergey back then was also part-time at Google
Right.
Brain. I think he was in the robotics team, so we were never in the same team. But the nice thing was that we could kind of collaborate with each other through that, through the fact that he was also at Google. So a lot of my PhD projects, which involved some amount of Google involvement, were like I think they do have, for instance, Sergey on them as well,
Right.
and a bunch of other researchers. But I did explore things involving like a lot more applications. Like we looked at some stuff with Amir, Yazdan, Babsh on some amount of sort of roughly speaking chip design, or what you can think of as accelerator design. So we wanted to optimize. What kind of components go on an accelerator or a chip? You can think of it roughly that way. I also got the opportunity to kind of I guess I don't have a paper on this really, but like to explore a little bit about like sort of the behavior of RL algorithms and sort of large scale recommendation systems. That was another thing that I got the chance to look at, and we were also looking at things involving games and large scale things. So a lot of it was kind of very synergistic with my PhD and sort of fundamental research we did at Berkeley or things I was doing at Berkeley. So it's sort of a very natural way to kind of collaborate and work on sort of similar questions.
Awesome. And after Berkeley, we sort of talked about how you were at Google Brain as a student researcher. So I'm assuming that there was definitely some door open to either go full time, not just at Google Brain, but really at any other place. And so you sort of face this decision of like, should I go to industry after graduating with my PhD, especially at Berkeley, which is in Silicon Valley, where there's tons of startups and tons of other big companies, versus go become a professor. And ultimately, you chose to become a professor at CMU. So maybe tell us a little bit about that decision, recruiting to become a
Yeah.
professor, and what motivated that.
Yeah, that was yeah, that's a more recent decision
Yeah.
I kind of remember fairly well. So back then, I guess already realized, I think kind of maybe somewhat midway in my PhD, that I was interested in like kind of more fundamental questions and
Yeah.
things involving sort of like kind of open-ended things which maybe we don't have a solution to. I think my research style also evolved a lot from sort of really methods-driven research, which was like, okay, here's a new method, and we show it works on some benchmarks, to sort of more, I guess, kind of a hybrid of like trying to better understand and study techniques that exist right now, as well as using those insights to now build better techniques. And I think that sort of is reflected a lot even in my current sort of research style of my lab right now. But a lot of that kind of required a lot of precise experimentation, but then also asking the right open-ended questions and setting the right experiments and hypotheses, as opposed to sort of like building the next method. And it seems like a lot of these kinds of like understandings and plus sort of building the next thing kind of research projects can be quite high risk, and they require a bit more sort of intellectual freedom. Potentially they don't even work in a particular, when you started off, but then 1 year later you realize that some aha moment came to you, and it might give you some insight about a previous question. So it just it seemed like I think a place which has sort of much more freedom to kind of do really open-ended blue sky kind of research was sort of a good place. That's kind of one of the reasons, and academia provides you that really, all the time.
Right.
The other thing was actually students. So I really like working with students and just collaborators more generally. I think I've probably collaborated with so many students at so many places at this point. Not necessarily people who are junior to me, but also people who are sort of peers and seniors who I've worked with, which has been quite nice, and that also seemed like a lot more doable in academia. So yeah, I think those were sort of the two main reasons why I was kind of leaning towards academia, definitely. I So the process of applying was, I think at the end of my PhD, I applied for sort of faculty positions. I did interview at a couple of schools, and then it seemed like out of all the offers I had, CMU was a very good place to be. Primarily because I think students are great here, resources are great. There's a lot more sort of collaboration culture across departments and things like this. So that's when I kind of joined here. I did take a gap year, so I was for a year right after my PhD. So I
Yeah.
deferred my faculty job start date to a year later, and I was full time at. I guess I had signed the Google Brain offer back then, but then I think that was the time when it merged into Brain and DeepMind got merged into one org,
Right.
and so then I started at Google DeepMind basically.
Gotcha. So maybe tell us a little bit about that experience. So, for a year you're working full time at DeepMind.
Yeah.
Walk us through some of the stuff you did there.
Yeah, of course, I cannot talk about the
Of
more
course.
technical things.
Of course.
I was so I had done a lot more like RL, sort of fundamental RL algorithms and RL techniques and things of that sort in my PhD, and I was kind of just generally interested in that. I still work on that. But then the gap year did provide me an interesting opportunity to explore their applications in sort of the language model context, which I hadn't done at all in my PhD. This is also the time. So the time when I was on the faculty market, I think ChatGPT had just come out. Like I think
Yeah.
it was December 2022, and I was doing my faculty job search in 2023, and that's like early 2023, and that's the time when I was thinking of graduating. So it seemed like there was sort of some evidence of like using RL in the context of LLMs and sort of really these open-ended systems, without sort of operating in very in sort of like fairly narrow domains. That was kind of quite exciting, and things that required scale and compute, which which at least during my PhD, it was not a requirement for academia to have that much. So I started working on things involving RL and LLMs in my role in GDM in DeepMind, and it was. I guess we looked at a bunch of problems, right from, for example, like the standard instruction tuning to things that became things around like sort of reasoning. So back then we wrote a paper with one of my with a student collaborator of mine, Charlie Snell, on scaling test time compute, and a couple of other things involving self correction and sort of reasoning and verifiers and things of that sort. So just yeah, a lot of things involving research in the context of RL and LLMs that was sort of done that year. Yeah, I don't know if I can go into too many more
No,
details,
that's fine.
but
Yeah.
that's sort of yeah.
Yeah, awesome. And thus far at CMU, you've been there since as we mentioned, right after your time at DeepMind. Are there any sort of notable experiences, maybe classes you've taught? Now you're leading
Yeah.
like the CMU AI and RL lab. Walk us
Yeah.
through some of your experience there.
Yeah, so CMU has been fun. Actually, I didn't. So Sergey had mentioned to me that the reason why he likes a faculty job is because it's a very sort of multifaceted job, and
Yeah.
actually I've been realizing what that means, and I think I like it for a very similar reason. So it's been great. So I've been teaching like deep RL. So it's I guess yeah, it's a I've taught both an undergrad version of that class as well as I'm right now teaching a graduate version of that class.
Right.
This time it's very big. It actually has I think right now I guess we are still in the middle of the enrollment process, something like around 240 students enrolled, which is
Right.
a lot for CMU. Um, but it's been the teaching has been fun because a lot of it is kind of areas adjacent to what my research has been on, which is nice. I've been trying to kind of sort of experiment with a few styles of teaching in the context of like how do I present a certain material? Maybe certain things are presented differently from what they were presented in the papers that build those things. So we'll see how that goes. But that's been fun. In terms of research, yeah, I have a lab. Yeah, my lab is called AI and RL lab. It's been fun because we have, I guess, I think I have 5 students right now, and they all work on sort of similar sort of technical questions, or they're interested in similar sorts of technical questions, but then the kind of domains they are working on are very very different. So, like for instance, one of my students is working on like real robots. One of my students is interested in sort of the core machine learning questions around RL. Two of my students have been looking at language models and RL. And the thing that I've kind of realized actually, and this is sort of something I think I knew that this was going to happen, but I think how synergistically this happens has been quite awesome to see, which is that a lot of the times sort of ideas from one domain or one context actually can shed light on problems in another context. So for instance, like we did something around LLMs, which you can broadly think of as LLM reasoning. And those sorts of ideas actually do tell you how to potentially do robot data collection better, potentially for like making robot RL a possibility that you can get to see in the near time future. Likewise, for example, some things which we did for robot data collection sort of have an analog in the LLM context, for instance, and that's quite nice to see because I think it then sort of gives you a conceptual way to solidify your understanding of like what is exactly the true insight that is enabling these systems to work, which is quite nice. And there's a lot more discussion and a lot more learning that even I have had because some of my students are experts in areas which I don't know much about, and I
Right.
think yes, it's good to learn that. So it's been so far quite fun in that regard. And then the students are great at CMU, which has been awesome too. So I think it's it really feels like sort of a very fast-paced research lab, and a lot of things to learn from my students. So that's awesome. Yeah.
Awesome, awesome. All right, so let's go ahead and deep dive into some of your papers. Let's go ahead and start off with offline RL tutorial review and
Yeah.
perspectives on open problems. Can you just tell us a little bit about this one?
Yeah, so I actually this was something that was done in 2020. I guess I mentioned earlier that when I started my PhD, I was looking at questions involving exploration, and I realized that it wasn't actually so exploration was a problem, but it seemed like we didn't even have algorithms that could learn from data that was already collected, and that's kind of the starting point when I started thinking about like this notion of like offline RL, meaning if I gave you a data set of experience, can I build learning algorithms, RL algorithms that could actually extract the most signal out of it to find policies that are really good. Given the data. So it's sort of like, suppose I have historical experience from a bunch of, like, let's say a bunch of robot data, a bunch of LLM training data. Can I actually utilize that to now build a better LLM or a better robot policy? This paper actually is more of a survey paper, which focuses on a bunch of like stuff that was happening in the field at that time. So this is from, I think, 2020. And it focuses on, it characterizes a bunch of algorithms that people had built for, including us, had built for like this question of like learning from static offline data. Um, this area was studied actually previously in the RL community and was called batch reinforcement learning.
Right.
But then a lot of assumptions that were made in batch RL back in the day were actually not very realistic. So they assumed, like, for instance, coverage over every single type of behavior you might want to optimize your system to achieve. But that is sort of a very unrealistic assumption. So what we did in this paper was I think I'd just written one of my papers called conservative Q learning. And it was sort of one of the most well cited papers I've written in my PhD, and that paper, for instance. After the paper, I think we realized we had a sense of like the taxonomy of different classes of methods. So we just wanted to put it together for the community. And this paper that you just talked about actually puts that together in the right way. I think that it's still sort of quite relevant. For example, one of my LLM collaborators who was doing some things involving LLMs and RL and was thinking about like offline RL in that context was actually referring to some of the sections of that like just a couple of months ago to understand a bit more about what this means in the LLM context. So if anybody's interested in learning from offline data, I think this paper still is a very useful resource. And we later did, so Sergey and I later did a tutorial at Neurops on a very similar on the same, I think it's titled in the same way as that paper. So that's like sort of a video version of that and a presentation version of that.
Awesome. I think in a very similar year, you had another paper titled Conservative Q Learning for Offline RL. Maybe tell us a little bit about the difference.
Yeah. Yeah, so that paper actually, yeah, that paper is one of the algorithms for offline RL. So, so if you think about, like, for instance, learning from offline data or from data that exists already, there's like kind of two challenges that come up. One is, first of all, I need to be able to find a way to like do better than the data. So my goal is to find a policy or a model that can really optimize rewards much better than whatever I've seen. But I really don't have access to an environment where I can run simulations or run rollouts because I just want to learn from this offline data. That's the problem setting of offline RL. So how do I actually go beyond my data set and learn when I'm only learning from that data set? That's sort of one of the questions that sort of comes up in just generally in offline RL. So what a lot of the methods out there do is that they sort of try to train and run the RL problem with like a constraint that says you should not deviate too far away from the data set that you've seen. And if you've seen this, like even methods like, for instance, reinforcement learning from human feedback kind of does this. So you don't want to deviate too much from your like base model while you're optimizing your reward function. So what this conservative Q learning paper does is that it builds sort of a recipe for solving this problem without which kind of alleviates the need for this sort of a constraint that forces you to not deviate too much from your base model. And it does so by like learning what we call like conservative Q functions or conservative reward functions, or sort of more, you can think of it roughly as like uncertainty aware Q functions in a way, uncertainty aware reward functions in a way that sort of already account for, that already penalize you when you're going too far away from your data. So you don't have to explicitly put this constraint of staying close to your base model that you started off from, or your base policy that you're starting off from. Why is this nice? Because in most realistic applications, for a user to define this constraint of how close you should be to a base policy or to your data set policy is very hard, and very restrictive, because in some cases you want to deviate away from that behavior because your base model doesn't have good behavior. So on the other hand, what we are doing now is we are absorbing this notion of deviation into the cost function or the Q function or the reward function, which kind of makes it a lot nicer in practice. So this paper, when it came out, at least at the time, like the benchmarks that existed, I think it did a lot better than existing techniques. Now, since then, I think there's been a lot of work in the community, and people have built methods that are inspired by similar ideas, but then maybe some of them are also not necessarily inspired by similar ideas that can do well. But this paper had a lot of impact because it was we can kind of we could kind of get it working on robots after this. Not just like we, but like actually back then a team at Google Brain also got it to work on robots. I think LinkedIn used this for some of the recommendation system work, and I think they deployed it in production. There's a paper they wrote on this as well, and that drove some of their metrics to be more positive than other methods that they were using. So there's been a lot of kind of practical adoption of these classes of techniques, which has been nice to see.
Awesome. And then I think you had another paper, D4RL, where you worked on like data sets for deep data driven
Yeah,
RL.
yeah. Yeah. So back then, when we were doing this, and this D4RL paper actually came right before the conservative Q-learning paper.
Right.
So D4, so back then, what we realized was that when we were working on this, it seemed like there are some interesting technical challenges in learning from data. But there was no like standardized way to just isolate this problem and study it. So actually, I have a paper before D4RL, which is called BEAR, BEAR. And that paper, it was sort of the first time I actually studied this question of like learning from offline data, but things were done very in a very ad hoc manner. Like I constructed a sort of a data set out of some by running some policies out of not necessarily any in any principled manner or any standardized manner, and just studied things on top of it. So what we wanted to do with D4RL was try to sort of standardize this practice of research in this area of offline RL. And I guess we constructed a set of data sets and benchmarks that everybody can kind of compete and update their algorithms on, so that we can kind of know which algorithms are doing better than others. It's sort of like the OpenAI Gym equivalent for offline RL, but in offline RL, you need to specify what data should you use as well, because you're learning from data as opposed to just simulations in an environment. And so we provide like a set of data sets and the environment. Again, it also is one of those things which has lived their life. So actually, D4R now there are better data sets than D4R or better benchmarks than D4R as well, because the community has really solved a lot of the tasks that exist in there. So we kind of needed like better tasks, and again, that's been nice to see because every benchmark should have a retirement period, and it's been quite nice to see all the adoption that has happened with D4R.
That's great. And you know, sort of as we mentioned earlier, you had a paper with Charlie on scaling LLM test time compute. So maybe this is slightly different. I mean, obviously it's loosely related to the same areas, but this one's more on scaling. Maybe just tell us a little bit about this one.
Yeah, so this paper actually was a very interesting collaboration. So back when we ended up, so when I was working on like when I started working on RL and LLMs, I guess one of the problems that seemed to be quite interesting was actually getting these models to potentially sort of implement. So I was coming from an RL background, so I was thinking about all of these as sort of policies in a way, like policies that take in sort of questions or prompts and like produce some responses or actions, and this is like state to action mapping in a way. And it seemed like in a lot of these settings, when we think about sort of really open-ended tasks, it felt like actually training policies which were sort of somewhat more I guess you can think of it as like non-Markovian in nature. That's sort of the technical term. Would kind of be a lot better. So, for instance, policies that can potentially think again multiple times or self-correct themselves and potentially attack a problem in a way. And that sort of this way of thinking. I mean, now it's probably well accepted with everything around reasoning models, and it's been done a lot better as well. But back then, it was sort of not something that we even knew whether it was feasible or not. So this was sort of one of the first attempts to like actually seeing how well can we kind of spend more actions, or spend more thinking time, or spend more tokens, or thoughts, or test time compute. That's sort of the technical term in the paper, to sort of do better in some ways. And the hope was that, well, if this sort of a thing could work, that means that actually training with RL of some sort to learn these kinds of models right away should do a lot better. And we saw that happen because of all the things around reasoning models, for example. So what we wanted to do here was just to understand how much do we gain from like scaling model capacity, which was sort of the conventional norm for scaling back then, train bigger models on more data, versus sort of scaling just this inference time sort of test compute angle, or scaling how much can the policy that you've trained already act in the world to do better and better, and which of these was more appealing. Because if scaling model size and data were the biggest factors, then it meant that we should put in more more effort in just scaling up pre-training for them further. On the other hand, this was better. That meant that we should put more effort into building sort of better ways to train models or post-train models to implement interesting behaviors in a way. So sort of like, I guess Charlie did a phenomenal job in that paper with like running the right things, comparing the right things, and it's a very analysis-driven paper. I don't think really even there's new methods per se in that one, but it was a very good study that at least convinced me that we should invest a lot more on post-training models to implement nuanced behaviors. And I guess now probably it's very. I mean, now we've seen like what this kind of a paradigm could do.
Right,
Yeah.
right. Yeah, for sure. Okay, so maybe the last paper that we'll get into before we get closer to the end here. You had a very recent paper titled Optimizing Test Time Compute via Meta Reinforcement and Fine-Tuning. Maybe just tell us a
Yeah.
little bit about this one.
Yeah, so it's actually on the on the point about how you can get models that can again reason for longer and do better, but at the same time, sort of the main premise or the main starting point for this paper is the fact that our current sort of the current ways of doing sort of RL training for reasoning models has been really sort of mechanistically driven in the sense that at least when you see, for example, the DeepSeek R1 technical report, it seems like or like the Quen technical report or any of these like open releases that exist, a lot of it is very much based on sort of like here's a basic thing we ran with like a final where like a model is allowed to think for very long for many tokens and you get like a final reward which is just based on whether you were correct or not, and that single scalar reward actually supervises the entire trace that your model is producing. So in a way this does not actually give you any way to control or even constrain what kind of reasoning the model is doing, because it could have produced all sorts of maybe potentially irrelevant tokens to sort of still somehow luckily end up at the right answer and be rewarded in the same way, as opposed to when it produced a really meaningful set of steps, it thought really carefully and in the right way of thinking about things with a strategy that is likely going to generalize to other problems and then get to the right answer. So there's no way to distinguish these two cases. And the main premise that we have here is that one of them is actually a lot better than the other. So, to the point about the test time compute paper that I was talking about, this notion of like getting models to implement nuanced behaviors, we know that behaviors can sort of generalize really well. But if I just somehow produce a set of tokens that end up in the right answer and incentivize the model to do that more, that strategy will not generalize well. So if I just get a model to produce random stuff, and reward it if it does so, then that's the very bad idea for like deploying the model in the wild when it needs to deal with really unseen questions. So the main premise here is to sort of formalize this notion of actually thinking about implementing behaviors or strategies in a model. And what this paper does is this paper shows that you can do so if you think about it from the lens of meta reinforcement learning, which is actually a sub area in reinforcement learning, which I did not explore much in my PhD because it was heavily tied with exploration, and I thought we could not even solve learning from offline data. But now I think it's a lot more possible. It seems a lot more possible to me because we in my lab we've worked on a couple of things in that area. So it uses principles from this area of meta RL to actually build a careful build a modification to these RL training paradigms for these reasoning models, such that they can learn like generalizable behavior strategies. And the method is very simple. I mean, it does some kind of clever way of like rolling out from your policy. So it does some kind of branch rollouts and provide some dense supervision in a way, but it does seem to sort of work much better. At least worked much better in the experiments we could do in academic compute. But also since then, I think there's been a couple of like larger scale releases from different companies which actually have a very similar idea in place, and they show again like the promise of this sort of a paradigm broadly is can be quite high even at like very big model scale. So that's been quite nice to see. So yeah, that's sort of the broad thing, like learning behaviors as opposed to just learning somehow to solve a question that you were given.
Awesome. So, sort of moving, closer to today, what are some of the areas that you're really excited about? Maybe some collaborations that you're working on, the ones that you're allowed to talk about, or areas that you think need a lot more innovation?
Yeah. Yeah, so I've been actually very excited about this problem of I guess like open-ended exploration in a way, or what I call discovery. So I what I would what I want to see, for example, from AI systems is like an ability to potentially act for very long and do better and better in a way. And in a way, like test time scaling is kind of an aspect of it. Where, I mean, you can think of it as acting for longer and producing a better answer and being more accurate. But what would it take to actually build models that can act for like days to months to maybe years, and they constantly even though they are not like really trying to solve a particular competition question, but really trying to make sense of like really vague goals that I gave to it. So for instance, like what would it take for me to build what would it take for us to build like a system which can take in a rough research discussion, for example, that I would have with my student, and can kind of act on it to produce some meaningful new knowledge in a way. So a system that can potentially creatively think about things, potentially sort of use its own experience to propose new things, and go and attack those kinds of tasks. Potentially that can come to me with like questions and confusions. Potentially can disprove itself when needed. Like a lot of these kinds of behaviors, I think they don't come out of training models to sort of on a data set of like questions and answers or questions and rewards, or just pre-training on tons of internet data. So how can you kind of imbue models with these kinds of behaviors? And there's technical questions around it, like there's infrastructure questions, like how can you even run a model for that long without it losing sense of its own context, to sort of what's an objective function that you would use to train such a thing, what's the right way to balance compute between pre-training for such behaviors to post-training to RL. And I guess this is sort of one of the broader questions I've been interested in. But then obviously, like a lot of the projects we work on, this cannot be one student's project. So it's been sort of like questions that we would need to enable such a paradigm sometime in the future, which includes questions like exploration, creativity, better post training, things like this. So those are sorts of like research questions that we've been thinking about. But this has been sort of one of the high level kind of vision type of things that we talk a lot about in my group. Yeah.
Yeah, so I mean, there's been a few recent pushes in the industry. One is AI for science. I think OpenAI has spun up a new sort of scientific division. We see a lot of startups that are now trying to target specific areas within science. Are there
Yeah.
any sort of like maybe industry applications of RL? We're also seeing, certain companies that are now doing sort of RL as a service or RL sort of fine tuning and things like
Yeah.
this. What are your thoughts on those areas?
Yeah, that's a good point. So I guess maybe this obviously I don't know much about what all these companies are doing. I guess so. A lot of it is just sort of hearsay in a way, or I mean, at least my knowledge is based on that. But at the same time, I do think that, like for instance, RL as a service could be quite nice, especially for. So my sense working in the area of RL and LLMs for like I guess now a year and a half has been that actually a lot of the results that you see from academia are to some extent at some level like conflicting with each other, and it's not a bad thing, right? It's maybe a good thing because we can then debate about it and figure out
Mm-hmm.
what actually went different. But at the same time, a lot of the times, to get meaningful results, we kind of need to really standardize a lot of things around details, which maybe not everybody is that careful about or even knowledgeable about. And even for us, for example, we have had cases where we thought something was working only to realize that it was working for some like other mundane reason, that some other like random reason that is like nothing to do with what we were actually trying to do.
Mm-hmm.
So actually having like service like RLS fine tuning or RL fine tuning type of services could be quite nice for academia, especially if you want to like make a concerted push towards
Mm-hmm.
getting results that we all believe in. So that could be quite nice, or at least standardization in that area could be quite nice. Even it could even be at the level of like here's a coherent RL code base that you can do everything with, and everybody or a big chunk of the academic community kind of switches to that and does things. That would be quite nice. In terms of like actually thinking about AI for science, I do think that like AI has a lot of potential for science, and I think if given a chance, I would actually want to like think about questions in that area as well. I'm not a domain expert at all, but I think I'll love to know more about kinds of domains that people are thinking about. But at the same time, I also do think that general AI systems do have a role to play here, and that's something that I kind of often get torn between. So if I were to, for example, try to solve a scientific problem, it seems like one can go in there and try to think about just that problem, but then it also feels like that a generalist system that is more capable of just generally doing research or generally thinking about open-ended things should probably be useful in the long run to solve not just that but many other problems as well.
Mm-hmm.
So I think I'm a little bit torn often between like sort of immediate term scientific AI for science research
Mm-hmm.
versus sort of long-term AI for science research. which where maybe the long term depends a lot more on getting the AI, getting the generalist AI to be capable of doing things that we probably would need for scientific research. I really don't have an answer to this. I mean, this is really just open-ended, vague thoughts. But yeah, I think this is sort of the rough thing. So I think it'd be quite nice to actually see industry impact and AI for science for even everybody to know what is possible. And yeah.
Yeah, there's also this large problem in RL of like how do you design the best verifier? Like we had
Yeah.
Rishab, who's one of the people that I think you grew up with at ITB, and I've collaborated with since. And so he was sort of talking about this problem of it's really difficult to get good verifiers. It's one of sort of
Yeah.
the big bottlenecks in RL. Verifiers are maybe one bottleneck. You have spent basically your entire life, the past decade or so, really dedicated to understanding as much as you can about RL, from the theory side to scaling, so on and so forth. What do you think are like the true bottlenecks aside from just verifiers, and how can we solve them?
Yeah, that's a great question. So I think that there's two bottlenecks. One of them is verifiers, which I agree with Rishabh on that. I will actually we collaborated till I mean, till a couple of months ago
Yeah.
when he used to be I mean, I collaborated with him during my PhD as well.
Right.
Yeah, so verifiers actually are a big thing, and actually verifiers, the more technical RL terminology for it is Q functions or value functions.
Right.
In my mind at least, they are very similar to each other. And building good value functions or building good verifiers is like a big open area that I think we should all invest in the RL community. I think maybe the only thing that I would so whenever I talk to people about building verifiers, a lot of the times the discussion goes into sort of what's the right data to train on. But I think we should probably also think about what's the right kind of input and output that we need from a verifier, which I think is a bit underappreciated. I feel in the at least in both the RL and the sort of like LLM or generative modeling communities. So in one case, it's oftentimes just like notions of correctness, and that's it. And that's sort of like what a lot of the LLM community focuses on when they think about a verifier. But it could also be something much more nuanced. Like it could be a piece of text. It could be something much more dense as opposed to just a number. It could also be something that is not just trained on existing data, but something else in some way. And I think that will be kind of a nice sort of area to explore in that regard. Likewise, in the RL community, I think verifiers or value functions just mean this one little object which you can write down a Bellman equation over and like trying to train it with like a certain class of methods called TD learning. But then again, you can probably do a lot more flexible things there if you leverage things like LLMs as your base models or in the picture in some way. So how do we kind of use our best insights from both of these areas to build really robust and generalizable verifier slash value functions? I think is an important question which I think the community should study more on. And some of my students have been thinking about these questions as well. The other question, which I think is also very important, is actually exploration and behaviors that my models learn. So I'm yet to see an example where, at least in the open source sort of space, where we kind of successfully got a model to automatically acquire a new behavior, which maybe it had never seen during pre-training or during all sorts of intermediate training that people do. Oftentimes, what ends up happening when we think about like getting these models to learn from their own experience or with RL is that these models end up amplifying and maybe somewhat chaining together behaviors, even that chaining or stitching behaviors that these models already know. This happens in a very specific regime, and I actually a lot of academic work in RL for LLMs does not operate in that regime, which is unfortunate, but it happens in a very specific regime. But I think like this learning totally new skills or being able to like do things which I'd never really that my model had never really seen before, or even never really seen anything similar to it before, but could learn this from its own experience, is something that I think we should look at. And in a way, like I think back in the classical days of RL, when people looked at like Atari games or grid worlds or all these types of domains, I think we could get policies that could like totally discover ways to play the game by starting from nothing. But I don't think that the LLM RL sort of regime operates, LLM or RL for LLMs operates in that regime at all. So what can we get it? How can we leverage both the flexibility of RL to learn such behaviors in general with the priors provided by these big, large generalist models to enable really kind of open-ended exploration of new behavior? That's another big question, I think, which we should study. And again, with this question, it's like the same thing. There's no actual benchmark that studies it because of so much contamination going on. It's very hard to even qualify if like certain behaviors are because of exploration capabilities or because of just seeing something like that in pre-training. But like being able to find the right way to evaluate and build such things is going to be also critical.
Awesome. So our very last question, what advice
Yeah.
would you give to researchers that are trying to come up with good research directions? Seems like you've made a lot of good choices throughout your career in research and, picking valuable areas of research to focus on as sort of the tides have shifted. And as, the research field continues to evolve, directions are always changing. There is this process of, deeply understand all the papers in the existing field and then think about some creative direction to pursue and then pursue it. And sometimes it works, sometimes it doesn't work. What are your thoughts there? How do you think you've been most successful?
Yeah, that's a great question. Well, I guess I don't know if I don't know if I'll have full advice for everybody out there, but some things that or some principles that I've learned over time doing research, which I think are useful for especially for new researchers starting in an area, is that the first thing which I found quite useful is to think about things from like first principles. So I think there's like tons of work, especially in like an area like RL for LLMs. There's tons of work which now focuses on small deltas around existing kind of methods and
Right.
stuff like that. But then I think I would recommend actually like people to think about like the broader question of like what are they trying to solve, and like even if they were to accomplish doing so, how would it influence things like 4 steps down the line, or if somebody were to build on that like for 4 like nicer things, like how would that push the frontier of where we are at currently.
Right.
I think that's something that I found actually very useful to think about when choosing problems to work on. That's sort of one advice to think a bit into the future as to what somebody would do if you were to accomplish what you wanted to do, and see whether you're happy with that or not. The other thing which I found quite helpful is to actually think about things from a more like problem first or bottleneck first perspective than methods first perspective. So as an ML researcher, I think the most natural instinct is let's try to build a new architecture or a new objective or a new training paradigm that's going to give me better numbers. And we are quite heavily benchmark driven. But historically, actually, RL has never been benchmark driven because benchmarks have been, it's not necessarily clear that benchmarks or environments were very standardized. So coming from an RL mindset to sort of things like LLMs, I think one thing I've been seeing more useful as LLM benchmarks get contaminated is to think about like properties that I want from a method, or problems that I want a method to solve, as opposed to sort of here's a method and gets me a better number somewhere. I think thinking about things in the problem first perspective without being tied to like a particular idea that you have for a method kind of really makes things better, because then it gives you a more holistic picture of whether what you're doing is actually useful or not, especially in a more kind of rapidly evolving field like what we are in currently. So I think thinking about like things more problem first, being maybe even like just playing around with existing things to find what the bottlenecks are, what things cannot be just solved by like scaling data or by just training a big better model or something else. I think those will really tell you what are the problems that actually will matter going down the line, and trying to work on that is sort of the best thing right now.
Awesome. Awesome. Well, thank you so much for coming on the podcast. Really appreciate it.
Yeah, thank you so much for having me.